Hi, Jan.
Hi.
All right. So I guess we need the microphone for you to hear us. So we'll when there are questions, I'll try to deal with that.
Perfect. Yeah, thanks.
Okay, so we're very happy to have Jan Sbierski give our second talk of the morning on the formation and inextendibility of weak null singularities. So take it away.
Yeah, thank you very much, Jakob, for the introduction and also for the invitation to speak. It's also appreciated that you made it possible for me to give an online talk. So Jonathan already gave us a very nice overview of weak null singularities in all their possible guises in relativity. So I will not spend too much on motivation and background, but I'll jump straight in. So let me first recall some basic facts about the exact subextremal Kerr spacetime. So this is a Penrose-like diagram. Here we have future infinity, time-like infinity, the Cauchy horizon, and the event horizon. So we will often use, as Jonathan also did, double null coordinates, so Pretorius Israel double null coordinates. So we have u bar goes to infinity in this direction and means infinity in this direction.
Could you maybe write a little bigger?
Sure.
Thanks.
So u bar like this. And u goes to minus infinity in this direction and plus infinity in this direction. So we also have the Kerr function appearing in the metric delta, which is r squared minus 2mr plus a squared, and we are in the subextremal regime. So this is the relation for the angular momentum per unit mass and mass of the black hole. And let me recall that the roots here at the Cauchy horizon, this is r equals r minus, and at the event horizon we have r equals r plus, and delta, which is negative in the interior of the black hole, this goes linearly to 0 at the Cauchy horizon. And if I express this in terms of the u bar coordinate, then this goes exponentially. Yeah, it goes like e to the minus kappa u bar to 0 towards the Cauchy horizon. Okay, and so now the result that Jonathan mentioned takes the following form. So I look at a characteristic initial value problem, where on one null hypersurface, which I should think of as the event horizon, I prescribe initial data which settles down to Kerr and is also close to Kerr on this hypersurface, and the transversal one, h bar 1, there I assume initial data which is close to the induced Kerr initial data. And then the statement was that I can find like a slab of this form where I have a solution to the vacuum-Einstein equations, and the metric extends continuously here to the Cauchy horizon. So I have a continuous extension, but I have no local Lipschitz extension to the Cauchy horizon. So, and I want to tell you a bit more about the proof of this this result. So it's divided in 3 steps. The first is the existence of the spacetime. Then the second is to prove the instability, so that we have some form of curvature blow up at the Cauchy horizon. And the last step is the inextendibility, how to prove the Lipschitz inextendibility. And so let me start with the existence part. And so this is work of Dafermus and Luke. As Jonathan said, it goes back to 17, and then also like a remaining bit from the event horizon to like a space-like hypersurface. So where you start from here and go to a space-like hypersurface in the interior. This is forthcoming work of theirs. And so the assumption which we assume here and also which they assume in their work, you can think of them in the following form. So these are weighted Sobolev norms, So U bar is our Eddington-Finkelstein-like coordinate, and Q minus is like a real number, which at this stage, later we will choose it bigger. At this stage, you can think of it as being bigger than 3. And then you need a finite number of derivatives. So I here is like a natural number. And then phi tilde. So here phi, these are metric coefficients or connection coefficients in a particular gauge. And so phi tilde here are the dynamical metric and connection coefficients minus the background ones. Okay, and then you have an integration of the spheres and the integration with respect to your null coordinate. So you want that this is close to, that this is small, so you have closeness to Kerr. And then you have a similar assumption on H1 where you just need closeness to Kerr with like a volume form, appropriate volume form on H1. So, and the statement is that if these assumptions hold, then for I big enough and epsilon small enough, space-time above exists with quantitative closeness estimates and continuous extension to CH+. So you have closeness and decay estimates here in the space-time. These closeness estimates, they degenerate up here at the Cauchy horizon, but you still have C0 closeness, which gives you the continuous extension up here. So this is the existence bit. Now, the second part is the instability statement. And so what is shown is that you have a curvature blow-up at the Cauchy horizon. So as Jonathan said, this goes follows from joint work of ours in combination with a result for the linear Tucholsky equation, or alternatively also, as he said, by very nice work by Guriaran, also from this year, who proves a related, very similar result. So in the following, I want to focus here on this work, and in a slightly unorthodox way, before I give you like a rough form of the statement, I already want to start with the proof. Somehow makes the statement slightly more convenient. So what we do is first we write down an identification, a global identification with the background Kerr spacetime. So we have here our dynamical spacetime. Here is M. I should delete this part here. Cauchy horizon, the event horizon. And so we write down an identification map phi, which identifies this slab with a slab here in the exact Kerr background. And on the exact Kerr background, we introduce a principal null frame. So here in the following, I will not always use the subscript Kerr, but if I have quantities which are underlined, then this is with respect to the background. So on the background, I have this principal null frame. It's a double null frame, which is normalized so that, so E3 and E4, these are the null vectors. They're normalized to be -2 with respect to the Kerr metric. And this principal null frame has the property that if you write curvature and some of the connection coefficients in this form, with respect to this frame that many components vanish. So it takes an algebraically simple form. And I still have the freedom to rescale these null vectors, and so the choice that we make is that E3 and E4, they are regular at the event horizon, but at the Cauchy horizon you have that E4 degenerates linearly in R, so like delta, and E3 correspondingly, since they are normalized, the inner product is normalized to minus 2, you have that E3 blows up, yeah, like 1 over delta at the Cauchy horizon. Okay, and now for our proof, it's important that we have something that we call the dynamical principal null frame on the dynamical spacetime. So we construct a frame E alpha, which we call the dynamical principal null frame. We don't need any particular important properties on this null frame, so we don't need to solve an equation to get that. But what is important is that this dynamical principal null frame, that this asymptotes or decays towards the background principal null frame. So if I pull back the background principal null frame via the identification map, then what is important for our proof that the dynamical principal null frame, when I look at the decay of the geometry towards time like infinity, that also this dynamical principal null frame asymptotes towards the background initial null frame. And this decay is exactly the same with which the dynamical metric G asymptotes or decays towards the background geometry. Okay, so we have this identification, we have the dynamical metric, we have the background metric, we also have the dynamical principal null frame, which has decay towards the background principal null frame. Okay, and now using this dynamical principal null frame, let me talk about the nonlinear Tarkovsky equation, which is the central equation that we use in order to show the blow-up of curvature at the Cauchy horizon. And so we write down this nonlinear Tarkovsky equation not in the Christodoulou-Kleinerman formalism, but we actually use the Newman-Penrose formalism. And let me remind you that this Newman-Penrose formalism is in terms of also a double null frame, but a complex one. So you have L, N, M, and M bar, where L is just E4, N is 1/2 E3, and M, this is the complex null vector formed out of the angular vectors. So this would be square root of 1, and then function C times E1 plus I E2. So it's a complex null frame. And here C, this is a function from the Kerr spacetime into the complex numbers, and it has unit norm. So that this here is indeed a complex null vector. Okay, and now having this frame, then by virtue of the vacuum-Einstein equations, you can derive the nonlinear. Yeah. Sorry, that was easier earlier. You can derive the nonlinear Tarkovsky equation, and it takes this form in the Newman-Penrose formalism. Here M bar, L, and N, these are just our derivative vectors. So you see that this here is a wave-like operator. Here psi naught is a curvature component which corresponds to alpha in the Christodoulou-Kleinerman formalism. So it's curvature evaluated in LM, LM. psi1 is curvature component which corresponds to beta in the Newman-Penrose formalism, and so on. So psi2 is also curvature component combining rho and sigma in the CK formalism. And all the other expressions here, so beta, alpha, pi, tau, and so on, these are all connection coefficients. So for example, we have that sigma is given like so. So this would, for example, correspond to the symmetric part of chi hat. Or mu is given like this. So this would correspond to the trace of chi bar and the antisymmetric part of chi bar, recalling that all of the expressions here in the Newman-Penrose formalism, they have two components, right? So they are complex. But then we also have connection coefficients which do not have a direct analog in the CK formalism. So for example, this one. And you see there is no direct analog of these connection coefficients in the CK formalism, since that one is tensorial. Yeah? So this is something without direct analog. And so on Kerr in the principal null frame, we have that many of these expressions, they vanish. So psi naught, psi 1 background, they vanish. The sigma vanish, kappa vanishes, lambda vanishes, and nu vanishes. And so now looking at the the form of the nonlinear Tucholsky equation, you see that all these terms here in these second and third line, they are all at these quadratic in terms which vanish on the background. So here sigma psi 1 or kappa psi 1 or psi 1 squared. So when you linearize this nonlinear Tucholsky equation, all these terms here, they disappear. So these we denote by n. So in a sense, these are the error terms. And so since psi naught appears in all the terms up here, this defines as an operator, which I denote by T2, acting on psi naught. So since psi naught vanishes on the background, when you linearize this equation, then what remains are exactly these expressions here evaluated on the background, and this is exactly what gives us our background Tucholsky equation. Yeah, this is this operator evaluated on the background quantities, and then at the moment it's just a generic reference linear field. So this is how the linear Tucholsky equation sits in this nonlinear Tucholsky equation defined on the dynamical space-time. Okay, and now with this terminology, I can tell you about the rough statement. So in addition to these assumptions which guarantee the existence of the space-time, so you should think of those assumptions as stability assumptions, we assume the following instability assumptions. And so these are assumptions on the nonlinear Tucholsky field. So this is the first one, and here Q minus, you should think of being epsilon less than Q, which is a natural number bigger or equal to 7. So Q minus is Q minus epsilon. And also that if you add a Q weight and you look at the projection onto L equals 2 spin 2 weighted spherical harmonics, of the nonlinear Tucholsky field psi naught, that this has limited decay in the sense that this is infinity. And furthermore, that if you take a finite number of derivatives and you look at the projection onto the L bigger than 2 spherical harmonics, or if you include a derivative with respect to the background time-like Killing vector field d by dt, which is space-like on the event horizon, then you get better decay. So if you have the same u bar to the q weight, then this here becomes finite. So let me make a few remarks about the these assumptions. The first one is that here in the stability assumptions, we had the weight of q minus 2. And so one should wonder whether this assumption is compatible with the assumptions that we make here. Since here, like these two assumptions together, you see, they tell you that psi naught has a limited decay, so there is a tail. This is related to like the tails that Jonathan talked about earlier in his talk. There is limited decay on the event horizon. And if you think about psi naught, which you should think about is in a certain gauge the same as alpha in the CK formalism, alpha you can compute from taking two derivatives of the metric coefficients. So naively, you might wonder whether going from alpha to the metric perturbation, whether you lose 2 powers of decay, right? Since, I mean, in these estimates here, we have a power of q minus, and then going to the metric coefficients, we only lose 1 power of decay, right? These are quadratic. You see that these assumptions are actually compatible with each other, since when you go from psi naught or from alpha to chi hat, or to chi, or to sigma in the Newman-Penrose formalism, then you have like a blue shift effect, which shows you that you don't lose a power of decay. So alpha decays at the same rate on the event horizon as chi. And then once you go from chi to the metric perturbation, then you lose 1 power. So this is computation you can do. So it shows that like these assumptions which we make on the nonlinear Tucholsky field, that they are compatible with the stability decay assumptions that we had earlier here. Okay, another remark. So this is compatible with 1. And also another remark which Jonathan already made is that when you choose q equals 11, then this is what we expect corresponds to the decay rate for generic solutions that are conformally regular at future null infinity. And when you choose q equals 7, then this is the slow decay that rises for these gauge Kerberger data, so which violates billing at future null infinity. Okay, and now under these assumptions, the statement then what we show is that if you take any outgoing null geodesic to the Cauchy horizon, and any small tubular neighborhood of this null geodesic, I call it V, that you then have that this localized weighted integral over curvature is infinite. And let me remind you that psi naught was defined with respect to L, and recall that L is equal to E4, and E4 degenerates at the Cauchy horizon. So we have that L degenerates like delta, so it degenerates from what I said earlier exponentially in U bar, where kappa is 0. So you see that this here is indeed an instability statement, since if curvature were regular, then even exponential weight should make this integral finite. So this is really an instability statement, that curvature with respect to a regular frame blows up. Okay, so this is the statement and what we prove. Let me now tell you a bit about how we prove this. So what we do is we introduce a linear reference field, and we want to show then that there is a blow-up result for the linear reference field, and then that the actual nonlinear Tucholsky field is close to this linear reference field, and thus it also blows up. This is the rough structure. Okay, and so now the linear reference field we define in the following way on the curve background. We define it as as a solution to the linear background Tucholsky equation, so with the underline, and the initial data I choose on the horizon to be exactly that of the nonlinear Tucholsky field on the horizon. And here I omit the identification map capital Phi, yeah, so for brevity. So I choose the initial data here to be exactly the induced initial data of the nonlinear Tucholsky field, and here on the transversal hypersurface, which we denoted h bar 1, I describe suitable data in h bar 1. So you can't prescribe here exactly like the induced initial data, since for the linear Tucholsky equation you have a blue shift here along the event horizon. So there's exactly one transversal derivative here on the event horizon, which you can prescribe, which leads to decay along the event horizon. So some of the suitable data on h bar 1 is fixed by our desire to get a regular Tucholsky field here in the neighborhood of the event horizon, so that the transversal derivative decays. Okay, so this now, solving this characteristic initial value problem, defines as our linear reference field on the background in the interior of the Kerr black hole. And now we consider a hypersurface gamma along which we have that delta, so which decayed linearly in R to 0 towards the Cauchy horizon, that delta decays like U bar to the minus sigma Q, where sigma Q is a positive number. So it's a hypersurface like this. Why we choose it, I'll tell you in a moment. But just recall that if you have a hypersurface of constant R here in this Penrose-like diagram, it looks very much like this hypersurface gamma here, like this hypersurface gamma. And along this hypersurface, R would be constant, so also delta would be constant. If you look at an outgoing null hypersurface, as we discussed earlier, then delta decays exponentially to 0 in U bar. And so this hypersurface gamma, it does go to the Cauchy horizon, so R goes to R minus along it, but it goes to the Cauchy horizon in quite a slow way, so that delta only goes to 0 in an inverse polynomial, with an inverse polynomial rate. And these hypersurfaces, which have this property, they were first introduced by De Fermus to the study of the interior of black holes. And now, having this linear reference field, we appeal to a linear instability result. There's also work on the linear Tucholsky equation by Gurriara from 24. So what we get is that along this hypersurface gamma, I can propagate these lower bounds from the event horizon. So I still have on gamma that the L equals 2 mode of the Tucholsky field, that this has limited decay, and the higher modes, they have slightly faster decay. Okay, so this is the instability at the level of the linear reference field. So now we want to show that the same kind of behavior persists for the nonlinear Tucholsky field. And so we look at the difference Tucholsky equation. And this will also explain to you why we choose this hypersurface gamma. So, okay, we want to show that psi naught behaves roughly like psi naught linear. So I look at the difference, call it psi, and also recall that we could write the nonlinear Tucholsky equation. You know that it took this form. So now if I compute, if I let the background Tucholsky operator act on the difference, then what I get is this expression, which I here at the right hand side I call f. And we see that this takes the form of a background inhomogeneous. Tucholsky equation with inhomogeneity f. Okay, and now the closeness of psi naught to psi naught lin we show by using a background energy estimate. And I'm slightly cheating here, but morally what I'm telling you is correct. So what we show is that if you know that psi on the event horizon is 0, so in particular it has very fast decay, and if I know that I have a good decay estimate for the source, so if the source also decays fast enough in U bar, this is less than infinity, where I integrate here over this region, this green region here, that then I also have that the difference field psi decays fast enough on gamma. And so once we obtain this, we directly see that this implies that star also holds with psi naught in place of psi naught lin. Yeah? So this would then give us that star holds with psi naught in place of psi naught lin. Okay. So the difficulty here is, of course, is showing that the source function has fast enough decay here in these directions towards time like infinity. So fast enough decay when U bar goes to infinity. Okay, and how do we show this? So there are various observations which we need to do. which we need to make. The first one is that each term in F is quadratic in difference quantities. So this you see, if we go back to the precise expression for the nonlinear Tucholsky equation, as I said earlier, these terms in n, they are all quadratic in terms where the background value vanishes, right? So like sigma is the same as sigma tilde, the difference with the background. Psi1 is the same as psi1 tilde, right? So all of these terms here in n, they are manifestly at least quadratic in difference quantities. Now here, by subtracting from the background Tucholsky operator, the dynamical Tucholsky operator, you see also that here you get a difference term everywhere, so that also these terms here are linear in difference quantities, and psi naught is manifestly a difference quantity. So also these terms are quadratic, right? So we have now obtained like a right-hand side which is quadratic in difference quantities. And these difference quantities, they come in two groups. Groups in group 1, they have polynomial decay in U bar, and terms in group 2, they also have polynomial decay in U bar, but multiplied by a term which blows up, like 1 over delta. Since, I mean, it's not just a stability problem which we are solving, but, you know, certain quantities actually become singular, right? So this is something which you cannot avoid. So you have these difference quantities, some of them blow up. Now, another observation is that there is null structure, which implies that terms from 2, they appear at most linearly. And now I can also explain to you the reason why we looked here at this hypersurface gamma, which approaches the Cauchy horizon, but at a very slow rate. Since like these terms here, which appear linearly and which blow up, this here now blows up inverse with the inverse polynomial rate, and this inverse polynomial rate can be beaten by the decay that we already have here. And so you see that this introduces an upper bound on sigma q. And recall, sigma q was the rate with which gamma approaches the Cauchy horizon up here. If you let it approach too fast, then delta decays very fast, polynomially, meaning this term blows up very fast and you can't control it. So somehow this estimate here, this goes only through if sigma q is chosen not to be too big. Okay, and let me also mention that these decay estimates here, they were first proven by de Vermeers and Luke, but we also need to improve those in our paper to get slightly more decay. Okay. There's another aspect which I don't want to mention in detail. So you see one difference to the CK formalism is also that you have these terms here, which are connection coefficients with respect to the angular vector fields. And of course, on the sphere, you don't have globally smooth vector fields. So somehow to estimate these terms, it's important in our analysis that we work with two sets of vector fields, the one is regular in the northern hemisphere and the other is regular in the southern hemisphere. Okay, and then, so now we have propagated the lower bound on the nonlinear Tucholsky field to this hypersurface gamma. So we have these estimates here with psi naught in place of psi naught linear. And then now in the rest of the proof, what we do is first we use the finite dimensionality of the L equals 2 mode space to localize the blow up in angular directions. So recall that here the L equals 2 mode, I mean, you have, it's 5-dimensional, right? M minus 2, minus 1, 0, 1, and 2. And for each of these spherical harmonic contributions, you have explicit angular profiles. And so now using this finite dimensionality, you can show that you must have non-vanishing contributions in each angular direction. So this allows you to go from gamma, which is a hypersurface containing all of the spheres, to localize that locally. To localize it angularly, sorry. And once we have the angular localization, then we propagate this blow up to V, where V was the small tubular neighborhood of any outgoing null geodesic to the Cauchy horizon. So we propagate this blow up to V using a transport estimate, so coming from the Bianchi equations, taking care of the oscillations. So this is where a lower bound on sigma q comes in. And to see this, how the lower bound comes in, again, what I'm saying is not quite what we do, but it's morally what we do. So we look at like this Bianchi equation, which roughly is of the form du psi naught, where recall u now was this null coordinate along the Cauchy horizon. So we propagate it in this direction here to V. So du psi naught, and then you get one of these factors of delta on the right-hand side, and then terms like tau psi 1 and other terms. And now in order to show that this profile, when you propagate from gamma here to V, is more or less unchanged, here again we use that delta has decay in the region to the future of gamma. And so in order to propagate the profile from gamma to V, you need that delta decays fast enough in this region up here, meaning that you need to choose the hypersurface gamma approaching the Cauchy horizon quickly enough. This results in this lower bound on sigma. And so both of these parts of the argument, namely the propagation to gamma, which imposes the upper bound on sigma, and this propagation along the Cauchy horizon, which leads the lower bound, somehow the punchline is that some of these bounds, they are compatible. So you can choose sigma q in exactly such a way that both parts of the argument go through. And what I also said here about the oscillations, what I mean by that is that, so we take the projections with respect to the projections onto the angular slightly spin-weighted harmonics, and the angular coordinates which are involved in these projections, you should think of them as being transported along the ingoing principal null directions. So, in these profiles, theta and phi are being kept constant along these ingoing directions. But now when you look at an outgoing null geodesic and this tubular neighborhood, then, in these coordinates, which are regular at the Cauchy horizon, you keep theta and phi constant along these outgoing principal null directions. And this is what we are all familiar with already from exact curl, is that you have like these two sets of null coordinates, which give you like a smooth extension to the event horizon and the Cauchy horizon, which creates exactly these oscillations. And so you also need to take care of them when you propagate in this direction. So this is what I wanted to say about the rough structure of the proof of the result with Jonathan. So now we have proven the curvature blow up at the Cauchy horizon, and so then the last step is the inextendibility statement. This goes back to works from 22 and 24. Let me just briefly or just roughly mention the structure of this result. So it exactly has the form that if along any of these tubular neighborhoods around outgoing null GD6 which go to the Cauchy horizon, if you have here if sufficient fast blow up of curvature, then no local Lipschitz extension across CH plus. And so in this way, these three results, the existence result, and then the instability result, which proves the blow-up of curvature at the Cauchy horizon, and the inextendibility result going from curvature blow-up to no Lipschitz extension, they combine the proof of the statement Jonathan mentioned. So in the last few minutes that I have, I want to tell you about an important ingredient in this inextendibility proof. And this ingredient is the following, namely that when you look at the C0 extension of Dafermos and Luke, this is a C0 extension in a particular coordinate system x mu. And the statement is that this coordinate system is actually quite well chosen in the following way, namely that if you restrict here to any small local neighborhood of the Cauchy horizon, and you assume that you have a local Lipschitz extension across the small neighborhood, where this is with respect to y nu coordinates, and you look at the identification map, which identifies this part of the physical spacetime without the boundary, without the Cauchy horizon, with this part of the physical spacetime without the boundary arising from the Lipschitz extension. So this identification map, the statement is that this extends to the boundary, so exactly here to the weak null singularity to the Cauchy horizon, and here to the boundary in the assumed Lipschitz extension. This extends to the boundary as a C1 diffeomorphism. And so the statement is that this differentiable structure of Dafermos and Luke was chosen in such a way that if you had any Lipschitz extension, then the C1 differentiable structure is exactly the same. So in particular, if you look at vector fields, up to the Cauchy horizon, that these vector fields are also continuous vector fields in the local Lipschitz extension. And this is a crucial property used for this proof, which works with curvature, since, I mean, we don't, somehow this proof doesn't work at the level of, you know, like a Kretschmann scalar, like a scalar invariant of curvature, but it works with curvature contracted with certain vector fields. And these are exactly, you know, when we had C naught up here with regular version of L and M, a regular version of L and M, right? So it works at this level. And somehow this C1 compatibility of the differentiable structures tells you exactly that if you look at this curvature evaluated with on vector fields which are regular in the Differential-Luke extension, then they also have to be regular in the assumed local Lipschitz extension. This is how an important step how this inextendibility result goes. And together with Peter Cameron, who's also in the audience, we showed last year that this property does not hold for C0 extensions. So if you now wanted to show that this weak null singular spacetime is even inextendable, say with continuous metric and Christoffel symbols in null2 log, then somehow this property that this fails. So we construct alternative C0 extensions where the identification map does not extend as a C1 diffeomorphism. So this is somehow the main problem in going below Lipschitz inextendibility across the Cauchy horizon. But let me conclude with some brief mentioning of forthcoming work with Peter Cameron. And please do ask him if you're interested to know more. So the statement is that if we go back to spherically symmetric weak null singularities, so Jonathan mentioned those in his talk, for example, arising from the spherically symmetric Einstein-Maxwell scalar field system, that such spherically symmetric weak null singularities, they are C0 W1P log inextendable with the following restriction. It's a significant restriction, but nevertheless, as spherically symmetric manifolds. So also the extension is assumed to be spherically symmetric. And here P is any number bigger than 1.